Welcome everybody. This is our first Rome Joint Astrophysics Colloquia. This is a monthly series of colloquia organized jointly by the University of Rome Tor Vergata, INAF OR, and INAF YAPS. It is an honor to introduce the speaker of today's colloquium, Professor Xavier Barkons, ESO Director General since September 2017. He received his bachelor and master degrees from the University of Barcelona in 1981 and his PhD from the University of Cantabria in 1985. He was senior research scientist and then research professor at the Spanish Council for Scientific Research, while also conducting research at Cambridge University in the UK. Professor Barcons started the very first X-ray astronomy group in Spain in the late 1980s, and his research has been focused on obscured AGN in the distant universe, the evolution of the AGN population, and the comparison of X-ray and optical views of AGN. He has been involved in several large astronomical projects, such as the XMM Newton Survey Science Center, XUS, ESO, and recently the Athena X-ray Observatory. Before becoming ESO Director General in 2017, Professor Barkons served with ESO in many different roles, including ESO Council President from 2012 to 2014, and he has dedicated significant effort to help progress major ESO projects such as ALMA and EELT. Without further ado, let's welcome Professor Xavier Barkons.
Thank you very much, Francesco, for the warm introduction. Hello, everyone. It's really a pity for me that I'm not able to go to Rome. This is always a pleasure, and I hope I will be able to travel there at some point and meet many of you. I see lots of colleagues and friends among the audience. And yes, I hope that we will have opportunities to meet again in the near future. So yes, my honor to open this series, this joint astrophysics colloquia in Rome, and I have been warned that the audience may be rather diverse, and therefore I will give a rather general overview of what we are doing at ESO, what our plans are for the near future. So for those of you who are familiar with what ESO does, you will find most of the talk uninteresting, but for others, it may be the first exposure they have to our activities. So please bear with me. So yes, what is ESO? ESO is, of course, the European Southern Observatory, or officially named the European Organization for Astronomical Research in the Southern Hemisphere. We're an intergovernmental organization founded in 1962 by 5 European countries. And the mission of the organization remains these 2 bullets. One is to build and operate world-class astronomical observatories in the ground, and the second one to foster coordination in astronomy and collaboration and facilitate the flow of information. We're a science-driven organization. Our main product is data. It's scientific data for science advancement. But of course, in the course of delivering data, we develop a number of things, and we produce a number of other societal benefits. And I will come back to this at the end of my talk, because I think this is becoming progressively important to be aware of. We're not alone in this game, not even inside Europe. There's a lot of other observatories and initiatives and participation in worldwide projects. And of course, we also have the space component. We have very good coordination with ESA in particular. And therefore, we play a central role in European astronomy, but certainly this is not like CERN, right, where CERN is actually the ultimate particle physics research infrastructure. Everything we do it well or wrong, but we do it in collaboration with scientists, with the community, with R&D institutes, and with industry. And I will show a few examples on how this works. So today, ESO has 16 member states. Italy joined in 1982, as you all know, plus a 10-year partnership with Australia on the Silla Paranal program that started in 2018, and that aims at bringing Australia as a full member of ESO during this period or immediately after. And I'm not getting the question about Brazil anymore, but I will remind everyone that we signed the accession agreement with Brazil in 2010, but unfortunately the process could never be completed, and I really don't expect it to be completed in any foreseeable future. To give you a sense of the size of ESO, there's about 750 people working in our staff, about 450 in Germany, another 300 in Chile. Our budget this year, it nears 350 million. That, of course, includes the contributions to build the extremely large telescope. Our headquarters are in Munich. This is where I am today. And our observatories are in Chile. And I already mentioned the European dimension, including science policy of ESO. Why Chile? Well, you know that very early on, after the signature of the convention in 1962, there was a search for a site to put the first observatory in the southern hemisphere. There were several candidates, actually two, and Chile was chosen. There was an agreement signed in 1963, a treaty with the government of Chile. This was updated in 1995 and further developed with site agreements which encompass all the observatory sites that we have. The latest one that we signed, it was for CTA, for the southern array of CTA, and this is the photo you see at the bottom of the slide. What you see at the top of the slide is, of course, an image taken from the space shuttle when it was, I think it was the servicing mission flying over Chile, and you can see an interesting effect in there where all the clouds are actually stopped by the Cordillera, by the Andes, and there's this Humboldt current in the ocean, which makes the water very cold, and that keeps that portion of the land, which is the Atacama Desert, incredibly clear in their skies. So this is a fantastic place to put an observatory, and this is actually where a number of observatories from all over the world are being erected or have been erected during the last 50 or 60 years. But of course, there's another component, which is that during these decades, Chile has developed itself into a power in international astronomy. And we like to think that we also had our little contribution in there. So this is a summary of the sites that we operate. On the top left, it's headquarters in Garching. This is in the north of Munich, really very close to it. At the bottom, it's our offices in Santiago in Chile. And then you can see in this map the position in the map of Chile on where our observatories are. And most of them are actually concentrated in the region of Antofagasta, the second region of the country. We are organized in what we call programs. We have a big one, which is called La Silla Paranal. This actually has 3 sites, one in La Silla, one in Paranal, the other one in Chajnantor with the base camp in Sequitor. This is near San Pedro de Atacama. Then we have a second program, which is ALMA. This is a partnership we have with other organizations, international organizations, also in operation. Then we have the ELT in construction, and as I mentioned before, CTA South is in design phase. Actually, it's in the preparatory phase towards construction. We have a number of other activities internal to the organization, and we also partner with some of them with the community. For example, technology development. We have R&D projects. We have science and engineering research and training activities of students and fellows. Outreach, all of these activities are part of our mission in a way, and they are there to support our engagement with the community. So just to run through quickly through our programs, this is the very first site that is established in the Southern Hemisphere. La Silla, this observatory is now 52 years old since it was inaugurated. Today we operate these 2 facility telescopes on the right, the 3.6 meter telescope and the new technology telescope, which is 3.5 meter. That was the first telescope in the world to have actually active optics built in, which corrects for the gravity deformations of the primary mirror in real time. And on top of this, we have a number of what we call hosted telescope projects. Those projects are normally run remotely by institutes in the member states, and we provide the support at the site. And what you can see here is this 3 mushrooms there called black gem. Those are to follow up transients. And at the bottom, you can see all the 3 telescopes called extras, which are to measure transits of planets in front of their stars. Still quite a lively place, despite the fact that there is very few people in there, and a very productive outlet, I would say, for the next few years. We're actually renewing the instrumentation of the 2 facility telescopes with state-of-the-art new instruments. One is NIRPS, radial velocity in the infrared. The other one is SOX, which is to do broadband spectroscopy of transients. There was a remarkable event in July 2019 that looks like a century ago, but it's not yet 2 years ago. We were blessed with a total solar eclipse. To my recollection, the 3rd time that a total solar eclipse passes through a professional astronomical observatory. The day was gorgeous, and it was really a breathtaking experience for most of us that will never be forgotten. This site normally has 50 people in there. That day we welcomed 1,000 visitors, including some dignitaries like President of Chile, ministers, and others. A very enjoyable day and an opportunity for science and society to meet. Okay, so this is Paranal. This is the jewel on the crown of ESO. This is in the region of Antofagasta, 2,650 meters of altitude. And you see this platform there that we had to slice from the mountain 25 or 30 years ago. This is about 130 meters across, and you can see these big 4 telescopes that altogether constitute the very large telescope, the VLT. They contain a telescope, each one of them, which has a primary mirror of 8.2 meters across. It's a monolithic mirror. That's very much the limit of how large you can build a mirror without segmenting it, without having it made out of smaller pieces. This is yet a remarkable technology wonder. This 8.2 meter mirror only has 17 centimeters in thickness, and that makes it possible to feature active optics, as I mentioned before. There's also this other 4 smaller telescopes, the auxiliary telescopes. Each one has a 1.8 meter diameter telescope inside. Those can be moved from one station to the other. And either these 4 smaller telescopes or the 4 bigger ones can be used to do interferometry in the near infrared, which is really a unique feature of Paranal and almost unparalleled around the world. We also have these other 2 survey telescopes, the VST, which is an INAF telescope that ESO operates according to an agreement that comes to an end next year, actually, and Vista, that was a contribution from the UK that ESO is operating. This is a 4.1 meter telescope. Paranal is operated as a single system. There's one single control room, one single engineering team, one single everything. So that makes the operation of all this compound very, very efficient and very powerful. And fantastic. More than 90% of the nights during the year we can observe. This is really unique, and you can see in the bottom picture a little bit of a threat that we have, which is this light contamination from some of the nearby mining compounds or the city of Antofagasta. But still, the fact that you can see stars down to the horizon, this is something that you don't see anywhere else in the world. I mean, having a very good view of the sky with a lot of air masses, this is really a unique feature of the site. Yeah, that's a picture of one of the unit telescopes, the 8.2 meter telescope inside its dome. And some of the equipment and the technology that we have. In particular, you can see in one of these big telescopes we have this laser guide star adaptive optics facility that is now working regularly, and that allows us to correct for the turbulences in the atmosphere and reaching fantastic spatial resolution from the ground, even better than Hubble Space Telescope, only in relatively narrow fields of view. On the top we have MUSE. This is a rather complex IFU, integral field unit instrument. It allows to do tomography of patches of the sky, and below we have pieces of the interferometer. Those are the delay lines where we combine the beams from 4 telescopes to make real interference, and then we fit this into the VLTI instruments. And you have one of the latest, which is gravity in here, which combines 4 beams and produces astounding images and spectra with absolutely amazing spatial resolution of the order of a few micro arc seconds from the ground. The way this works, the way Paranal works, is that we at ESO build the telescopes and all the infrastructure. Of course, we tended the work to companies and to industries, but we are responsible for this. And then the instruments, the instrumentation that we have, this is developed in partnership with consortia of R&D institutes in the member states. And the deal there is that we provide the capital investments. Essentially, we buy the hardware, and the institutes provide the effort, the work. And this effort is compensated by guaranteed time observing. So the institutes, the consortia, get in compensation for their effort a number of observing nights. At the end, we operate, we own the entire facility, the instruments, everything, and we operate it to a very low technical downtime. Today, of course, barring the COVID matters, our technical downtime is below 3%. Of course, that requires technical work and investment, but it is worth. So we make sure that when we are on sky, we're actually collecting data. I've spoken about COVID briefly. I don't want to go into this. This is all I'm talking about these days, and I'm a bit fed up of it, but okay. So, of course, COVID had a big impact on ESO as everywhere else in the world, specifically on the observatories, on the Silla Paranal Observatory. We had to essentially shut down. We went into safe state in March 2020, meaning that only a very small team could be kept on site to just keep the vital systems alive, but we had to warm up the instruments and switch off the telescopes. It was almost 6 months later that we restarted some observations. It was actually on the 13th of September when we were able to open one of the VLT domes again with only 30 people. There's normally 150 people in there. And we started observations with selected telescopes. As the situation improved in Chile, we managed to move ahead and to include more and more telescopes and instruments into our observations. We reached what we call restricted operation in January this year, meaning that all telescopes and all instruments were available and they were all observing every night. Unfortunately, the situation deteriorated in Chile again in April, and we had to step back to what we call minimal operations, which is that only a fraction of the telescopes can be operated. But we're now again into a ramp-up situation because the situation is improving again. So today, actually, since Monday, the turno shift in Paranal, it's about 55 people, and we will be observing with either 3 of the 8-meter telescopes or with the full interferometer, which is in the right direction. Here's some pictures of how we're working in there. We had to do some urgent technical interventions even during the pandemic, but of course major technical issues and most of the commissioning activities we had to delay to better times, probably 2022. We lost a full semester of observing time. That was very sad, but in the last 6 months we've managed to do a lot of observations, almost as in a normal semester. The weather has been really great during the period 106, which runs from 1st of October to 31st of March. And that was really very, very good to see the photons flowing through our pipelines and being delivered to the users. So we, sorry, this slide is misplaced, but okay, maybe I should go to the next one. We do have a very lively program of renewing and updating the instrumentation in the observatories. That's called the Paranal Instrumentation Program. For those of you who are familiar with it, here's a list of the activities ongoing now. There's always new instruments in various phases of development, from phase A to almost integration and commissioning. So this year we have managed so far to commission 2 relatively simple instrument upgrades. This is CTA-S. This is a high-resolution infrared spectrograph, and IRLOS, which is actually a facility that enables adaptive optics 2 magnitudes fainter for moons. Sorry, for MUSE, for the MUSE instrument that I showed before for the IFU. Next year we will install and commission ERIS, hopefully moons as well, a multi-object spectrograph, and the year after foremost yet another multi-object spectrograph. And there's also a lot of other projects starting now. Now, this is one experiment that we had to do this year because traveling to Chile, it's incredibly problematic at the moment. I have to say that during the last year, only 3 of us, including myself, have managed to travel to Chile from Garching. So we did an experiment which was try to commission a new instrument remotely. And this is the image that you have on the top left of this slide. This is a facility that we have in Garching called Garching Remote Access Facility. What you can see here is not simple laptop screens. They are telescope control consoles. So you can actually move the telescope and operate the instruments. And this is how, with some support from the people in Paranal, with a very few people there, we managed to commission this instrument, the upgraded version of CTA-S, and also IRLOS. And this is really a tribute to the teaming between the people here in Garching, the remote work, and the few people that were available in Paranal. Actually, CTA-S Plus has been offered to the community already, thanks to that commissioning. Okay, this is how we envisage the suite of instruments of Paranal in the next years. This, as I say, always some renewal. We normally initiate a new instrument every other year, and we do an upgrade in the years in between. Okay, ALMA, that's our other big facility in operation. This is the largest submillimeter radio interferometer in the world. It's in operations now for almost 10 years. This is really a partnership where ESO is one of the 3 big parties. Well, 3 parties, NSF, the National Science Foundation in the US, it's the other one, and then the National Institute for Natural Sciences in Japan is a 3rd party. And of course, it all goes with cooperation with the Republic of Chile. So this is really a unique interferometer. It sits in the Chajnantor Plateau at 5,050 meters of altitude. It has 66 antennas that can be moved by means of 2 transporters over a plateau that is 16 kilometers in span. In this little building you have down there, this building is partially pressurized inside. Remember that the air pressure at 5,000 meters altitude, it's half of the one we have at sea level. And there we host the local oscillator, the correlator, which is the brain of the observatory, and a few other facilities. Although the bulk of the operations, we do it from 3,000 meters near San Pedro de Atacama. That's another picture. You can see again everything here, and at the corner you can see Apex, which is the part of the La Silla Paranal Observatory that I didn't talk about. This is a single dish, 12 meters in diameter, equipped with state-of-the-art instrumentation, and this is yet another partnership that we have with the Max Planck Institute in Bonn and with the Onsala Space Observatory in Sweden, and that project will end in 2022. Some of the infrastructure we have in ALMA, here's the transporters moving these antennas. Those are about 110 tons in mass, and the transporter is a bit heavier, of course. This is the correlator, an incredibly powerful computer tailored for the purpose of combining the data from the 66 antennas and some of the infrastructure that we have at 3,000 meters. So ALMA also had to switch off, of course, in March last year, but it had to be switched off fully in principle. So the coming back to operation has been much harder. It started in October. We had to ramp up the operation support facility, power up everything, inspect the antennas. They are in a very harsh environment. Some repairs had to be done. And thankfully, 1 year almost to the day in accuracy, we were able to restart some observations with ALMA and resume the cycle 7 observations that had to be interrupted. As of tomorrow, I believe, we should be back into what we call baseline science observations, which is more or less doing science observations as normal, but of course with much less people. That has been also a bumpy road because of the pandemic conditions in Chile, but we hope that this is sustainable over the next weeks and months. Again, some photos on some of the interventions that had to be done. Now the ELT, this is our major project that we're working on its construction at the moment. It will be the largest optical infrared telescope in the world with a primary mirror of 39.3 meters across in diameter. This mirror will be segmented, meaning that it will consist of 798 pieces of glass, of polished glass, each one of them 1.5 meters across, and they of course have to behave like a single mirror for the telescope to work. The ELT will bring really transformational science objectives from exoplanet search, exoplanet atmosphere research, black holes, very early galaxies, the first galaxies to shine in the universe, and many other transformational science objectives. Construction started in 2015, and at the moment we are of course being hit by COVID and many other aspects. So we will come with a revised schedule when we are confident about it. For the time being, our latest official release was first technical light in 2025, but we know that this will have to be updated. The additional cost for ESO to build this big facility, it's 1.3 billion. Of course, there's a lot of contributions from the normal, from the regular ESO support and the organization. And there's also additional contributions from the member states through the R&D institutes who are developing the instruments, and that will be rewarded with guaranteed time observing. The ELT is being erected in Cerro Armazones. This is only 20 kilometers on a straight line from Paranal, on a straight path from Paranal. It's about 40 minutes driving, and it will be operated as an integral part of the Paranal Observatory, together with the VLT and the VLTI. And we have started now a program called Integrated Operations Program to adapt and to move Paranal into a lean operations model that allows these combined operations of the two facilities. So this is very much how the top of Cerro Armazones was for the last months. The work on the site had to be interrupted in July. It's now being restarted with some fixes in the base cam and in the high side. There's already actually a couple of cranes in there, and now I hope that that work will restart. There's already staff waiting in there to be integrated into this gigantic foundation. This is, by the way, 110 meters across, and this is for the auxiliary building. This is where the dome will sit, and in the inner part it's where the telescope structure will sit, and that's about 55 meters across. So quite a gigantic beast. And as I said, this will be operated as part of the Paranal Observatory and the technical facility to support the ELT for illuminizing mirrors and so on. This is actually already being delivered, and we already own this technical facility, and it's sitting in the Paranal Observatory. Just to flash a few pictures to show you that there's good manufacturing progress in Europe with the optics, with the mechanical devices, with the sensors, with everything. This is our integration hall here in Garching, where you can see this test bench for the primary segment. You can see the 6 petal dummies. Those are not real glass segments, where we test the control and the position actuators and everything. Just to give you an idea, this is about 1% of the total collecting surface of the ELT. But of course, this is there for the testing purposes. The instrumentation for the ELT on the day 1, it will have 3 instruments. One is called Mikado. The other one is called Harmony, and the other one is called Metis. Maori, it's an adaptive optics feed for Mikado, and those instruments are in various stages of their development, and most of them are already starting their final design review, meaning that they will start cutting still very, very soon. For the next generation, there's 2 instruments at the moment foreseen. One is high resolution spectrometer. It has already been recommended by our high-level scientific and technical committee, and we're now discussing how to bring it forward, which I hope it will happen in the next few months. And after that, we will also have a multi-object spectrometer to follow. We had released a few months ago a totally updated and fresh website for the ELT. You can have a shortcut there by typing elt.eso.org, and it's incredibly informative, very updated, very helpful. It has information about everything. I do recommend you to visit this site. Now, just one word about CTA that I already mentioned a few times. So we're not building CTA. CTA will be built by an ERIC, by an European research infrastructure consortium that it's being constituted now by a number of governments, by a number of member states and ESO. We will be an 8% partner of this ERIC. The CTA will have 2 sites, one in the north in La Palma, one in the south in Paranal, in the Paranal territory, not in the mountain, but in the territory that it's next to it. We are working towards securing the conditions for the construction, in particular the funding from the member states. And we expect that we will start the construction of some of the infrastructure in the southern side later in this year, in particular the access road, and maybe also the connection to the power substation that it's already in there. Okay, I mentioned technology development. Here's just a sample of some of the projects that we are doing. They are very diverse in scope. They are meant to support our activities. For example, I just want to mention the first one, the facility for infrared ray tests that we have developed in-house. And actually, thanks to the agreement we have with ESA, we're exporting this to ESA as well, because they are also interested in this. We have a very active program on lasers and adaptive optics, on laser development. Actually, you may know that all this technology for the powerful lasers that all telescopes use now was developed at ESO some time ago. Of course, there's companies that exploit it now, which is fine, and many other technology development programs, including this other one with ESA, which is about curved science CCD detectors. We put some effort into developing and maintaining and curating our archives, the Science Archive. This is a very helpful facility. I'll show you in a minute why. Yeah, I mean, one of the latest achievements has been to integrate the archives of the Silla Paranal Observatory, so the optical and near-infrared data, with the ALMA archive. So you can enter this portal and get both the optical and the sub-millimeter data for your target source. That's really very helpful, and the user community really appreciates this a lot. So this is the scientific production that is enabled by ESO, by our facilities, measured in terms of refereed papers per year. We have been now living in this 1,000 plus papers per year since 4 years now, which is really a very healthy regime to be in. And you can see the contributions from the various telescopes and observatories that we have. So only the VLT and the VLTI in Paranal, they generate about 600 papers per year. ALMA is, of course, still in an increasing phase, although now it's more or less leveling off. Remember that ESO only has 37.5% of ALMA, but still a very productive contribution, almost 400 papers. La Silla stays at around 200 apex, very modest, and so on. Important point here to underline, about 30%, 35%, of course, of these papers are making use of the archive, of the science archive. And out of those, about half of them only make use of archival data. So they do not require any additional observation, which gives a second chance to all the data to produce science. It would be impossible to run through the science highlights of ESO in the last 60 years. So I will flash only and here about 2 or 3 of them, and yeah, I mean, just recommend that you look at our archives. In exoplanets, we have been providing a lot of data, very helpful, very many breakthroughs through it. Just showing these 2 examples. One is a radial velocity measurement that enabled the discovery of Proxima b. The one below, it's a transit observation around TRAPPIST-1, which has 7 planets in orbit, and you can see that there's 3 of them crossing at the same time in this one. Those are 2 of the main techniques to detect exoplanets, but we have also pioneered actually the imaging of exoplanets, and in 2004 a team obtained the very first image of an exoplanet. Of course, this planet, it's something like 2 times more far away of the star than Neptune from the sun. And last year we actually even enabled the first 2 exoplanets around the same star to be imaged. So that's a technique that we can also support thanks to our adaptive optics systems and the high contrast imaging that our infrastructures provide. I need to remind you that the Nobel Prize 2019 was partially awarded to Michel Mayor and Didier Queloz. You can see them here with the La Silla 3.6 meter telescope in their back. The discovery of 51 PEC-B was not done at ESO, of course, but I mean this group, Michel and Didier and many others, they discovered actually tens, even hundreds of exoplanets using radial velocity techniques with an instrument that they developed, which is called HARPS, and it's still very much alive and operational in La Silla. Yet I cannot skip this one, the identification of this gravitational wave event that went off in August 2017. What you can see in the right-hand side, which is what told us that this was a merger of 2 neutron stars producing lots of heavy elements in there. It's actually in a paper led by Elena Pian, and that took a sequence of very broad wavelength spectra using one of our instruments during a number of days after the event. What you can see here is the lag with respect to the start of the event, and you can see how this black body goes away, and at the end of the day you're able to identify lots of things with the lines that you can see in this spectrum. So that was really very nice work. And yes, indeed, last year the Nobel Prize in Physics was also partially awarded to work that was done with ESO telescopes, in particular the discovery of the supermassive black hole at the center of our galaxy by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics and Andrea Ghez in California. This is not exactly, again, what they were given the Nobel Prize for, but this is more recent work on Sagittarius A star, on the supermassive black hole, where the group from Rainer Genzel has been able to measure first the gravitational redshift of a star, of the star S2, which orbits this black hole every 16 years, and showing that it fits the predictions of general relativity very accurately. And only last year, 2020, they were able even to measure the precession of the orbit of this star with the instruments that are in Paranal, and that actually they built together with ESO. Gravity is the one that I showed before. So yeah, more science. This is protoplanetary disks where we believe planets are being formed in these rings. That is one of the promises of ALMA. That's why ALMA was built in part, and it's very nice to see that, yes, indeed, when you do this high resolution imaging of these protoplanetary disks, you see these rings that were predicted in the past. And what can I tell about this fantastic image of the first shadow of a black hole? This is actually a supermassive black hole in the center of M87. It's 6.5 billion solar mass black hole where everything fits very well. And of course, this was done by the Event Horizon Telescope using 7 radio telescopes in the world, including ALMA and APEX. And you can see on the right-hand side what the look would have been without ALMA and APEX. So that was really a very, very nice result. And here's a more recent one with the electric field lines, which is what you see in the image. Of course, that maps the magnetic structure, which is perpendicular to it. And I also wanted to flash yet another interesting recent discovery about an interstellar comet, an interstellar visitor that we had in the solar system, which apparently is the most pristine material we have ever found in the universe. We are doing a lot of engagement activities with the community, and we have enhanced those during these pandemic days. They want to advertise here this Hypatia Colloquium. This is a special series of talks, of sessions that was heavily oversubscribed. There we invite early career astronomers to make a presentation about their research program. This happens every Tuesday at 3 p.m. It consists of 2 talks, 20 minutes each by 2 early career people, plus 10 minutes for questions and answers. This is a total of 21 sessions. Sorry, we had to say no to a large number of people. This is live on YouTube. I do recommend you to participate, especially if you are interested in hiring brilliant people, and you will see many of them in there. Outreach and communication, we do a lot of this. We spend quite a lot of effort in reaching out to society about our scientific discoveries, and this is one of our particular initiatives here. This is the ESO Supernova Planetarium and Visitor Center that we have here in Garching. That was a donation from a private foundation, the Klaus Tschira Stiftung, here in Germany. We opened on April 2018. We had a lot of visitors so far. This number is not updated, but the monthly rate in a normal time, it's from 5,000 to 7,000 people. We have brilliant planetarium shows, and the exhibit is really very, very good, very informational. We also do teaching training programs, not only for teachers in Germany, but this also coming from Italy, from Austria, from Denmark, from the UK, etc. And actually, the Supernova is reopening today after having been closed for a few months now. We released recently a report, a brochure called ESO's Benefits to Society that you can find in our webpage. This is to emphasize what are the benefits that we deliver to the taxpayers and to society in general beyond pure science. And there's a lot of it, and we made an analysis, and there's a lot of benefits. Of course, science is our primary goal. We also develop some engineering standards. Some of them are being reused later by industry, and this is all an additional benefit. We mobilize the economy, the high added value companies and innovation. Our requirements for the companies that work for us are really terrible. but that helps them to prepare for the market, and they normally take good advantage of this. We do a lot of talent development. I mentioned studentships, fellowships, internships. We do all of this because we think it's our duty towards the member states, but also we want to contribute to having a very well-trained population of scientists, of engineers, and of all the capacities that we need to operate the organization and to support astronomy. Outreach and education, I have already shown. We do have a lot of initiatives in there. We do press releases, announcements. We have our image repositories. There's no book in astronomy in the last decades that doesn't contain an ESO image. And finally, but not least, we're contributing to international policy issues. And in particular, one aspect we're very concerned about, it's about the light contamination by these mega constellations of satellites now. And we're working together with many other stakeholders to try to keep this under control. So I'm nearing to the end of my presentation. How does ESO work? Well, for us, it's very important to have the capability of doing multi-year planning. This is part of our governance model. It's part of our convention. We can embark on very ambitious projects that will take 10 to 15 years to develop, like the ELT now, because we have the commitment of the member states and because the governance model foresees that this is something that will happen. This is not achievable by a single country, and we see it challenging in other forms of multilateral international agreements, even inside Europe. And I won't quote any examples here, but at ESO we have an incredibly powerful cooperation model with the member states that I really don't want to change by any other one. A rule of thumb here is that this has always to be a win-win with the member states. And there's a rule of thumb here which says that the member states get as much benefit as they put into ESO. So if you have a powerful scientific community, you will get a lot of observing time. If you have a very well-trained industry, you will get lots of industrial contracts. And that's the way it works. It's all competitive, but it's working very, very well. I'll give you just one example. The construction of the ELT only, it will place about 1,060 million euros worth of contracts to companies. I mean, I have to say that almost all of them are already in place, but this is really a major investment. And yes, indeed, this is the other part of our remit, which is cultivating links with all the sectors in our member states. Okay, so I think I've come to the end. I will leave this slide up, but I really don't think I want to comment any specifics on this because I have said it all already. So thank you very much.